Hi everyone, today we will be solving the Dijkstra's algorithm. Dijkstra is the shortest path algorithm to find the shortest distance between between one node and any other node of the graph. So here we are having an example of a directed weighted graph. So first we'll solve the problem here on whiteboard. Then we will solve this problem using we'll solve this problem, then we will code in JavaScript, and we will see at the end some practical use cases of this algorithm. So this is the example. Here we have multiple nodes A, B, C, D, E, F. These are the weights you can see. So I will show you the table first, so we will get more idea like when I will talk about how to solve it. So here what we important first need to take care is we will have a table where we will store all the nodes. We can see A, B, C, D, E, F are the nodes. Then we will have the distance. So distance represent the distance of that node from the source. So this is the minimum distance of that node from the source. So when we talk about the distance of node D here, so it will be the distance of D from the minimum distance of the D from the source. As you can see, I have written also distance is minimum distance from source of that node. So we have this unvisited node array kind of thing. So you can see all unvisited nodes. Now if we look at the steps, what we'll do is, first step is find the smallest distance among all unvisited nodes and pick that node. So initially we have to mark them as infinity. Okay, so we know the distance between source and to the same node will be 0. Okay, we will leave the third field empty. Via, so via is what's the previous, from where it's coming. Okay, so if we look at the steps, steps are find the smallest distance. So if we see, let's say we pick if we see all our unvisited nodes, the minimum distance is 0, so we'll pick the node A. Visit all its neighbors and update minimum distance. So we will go its all the neighbors of that node and update the distance. So if that current node is let's say if the current node is n and j is the neighbor, so we'll calculate the distance of that node, current node n, we are visiting the neighbors of n, so distance of n from the source plus distance of n to j if it is less than what the distance of j has in the table. Okay, for example, distance of d is already there, we'll visiting neighbors of b. Okay, so if that distance is less, we will simply update it, and we'll update the via field also. Mark the current node as visited and keep repeating it until we don't have any unvisited nodes. So let's start this. As we have the first step, as we have already updated distance first, so this is we can update it. Now the minimum distance among them is 0, so we'll pick the node A. Okay, so we know the distance of A is 0. Okay, so now A has neighbors B and it has neighbor C, only 2 neighbors. Okay, now if we use our algorithm, so that A plus, now distance between A and B is 1, and distance of B in the table is infinity, so 1 less than infinity, so that is true. So we'll update go to our table and we'll update the distance of B to 1, and what is the current node, whose neighbor we are visiting, A. Okay, simple. Now we go to C, same 0, distance of A is 0 plus distance between A and C is 5, less than distance of C at the table is infinity, that means 5 less than infinity, again true, correct. So we'll go to the table, go to the C, distance is 5, we need to update 5, and the current node is A. Okay, so we'll update A. Okay, I think this, as we have done, once this is done, no more neighbors, we'll mark this as, we'll remove from unvisited. Now if we see, so let's say mark this as visited. Now from the remaining nodes, which node has the minimum distance is 1. Okay, so now we are picking the B. Now we are picking at B, so distance of B is 1. So B has neighbors E and C. Okay, E and C. So 1 plus distance between B and E is 7, less than distance of E is infinity, so 8 less than infinity. Okay, so for E we will update distance is 8 and the current node is B. Okay, if we go to C, 1 plus distance between B and C is 3, less than, and what's the distance of C is 5. So if you see here, 4 less than 5, so this is a better path from to source to C via B. So we go to C, we will update it as 4, and what's the current node? B. So we will update this as B. Okay, because that's the current node we are doing. So still we are able to apply all our operations. Okay, now let's actually remove all these ones. I mean, like, we are erasing it so that we can see everything in the same screen. So like B has marked, we have like everything done. Yeah, so we will remove B from here. So B is also gone. Now if we see from the remaining nodes, which is the minimum distance is C. So we will pick C. Distance of C is 4. C has neighbors. Now E and D. If you see, C has only neighbors E and D. Okay, so we'll update 4 plus distance between C and E is 6, less than distance of E is 8. Sorry, 8. Okay, so 10 less than 8, of course false, so we'll don't need to do anything because we already have a shorter distance. Now if we go to D, so this will be 4 plus distance between C and D is 2. Okay, 2 less than distance of, if you look at distance of D is infinity, so 6 less than infinity. Correct, so we'll update the distance of D. We'll go to D, we will update as 6. What's the current node? C. Okay, so again the C has visited all its neighbors. C remove, here also. So now we focus on going to the next node. So what is the now node with the minimum distance is D. So we'll pick D. Distance of D is 6. Okay, D has neighbors B and E. Okay, so 6 plus distance between D and B is 2, less than distance of B is 1. So 8 less than 1 false, of course. So we are not going to do anything. Now if we look at E, 6 plus distance between D and E is 1, less than distance, what is the distance of E in the table is 8. So 7 less than 8. Correct, so we'll update the distance of E. We go to E, we'll update distance as 7. What's the current node? D. So we'll update at D. Okay, so this is also done, so we can, I think, keep it as last. We remove D. Yeah, so let's remove again. So if you see, we just need to do anything, we just keep repeating these steps. If we keep repeating these steps, then let's quickly do it for E. Yeah, now we are picking which is the smallest node is E. E. Distance of E is 7. E has neighbors only F. Yeah, D. If you see, E has only one outgoing, that is F. So it will be 7 plus distance between E to F is 2, less than F is infinity, so 9 less than infinity. Correct, so you'll update the distance. and we'll mark as 9 via E, and we'll remove E. This is also gone. Now the last node is remaining F, so we'll pick F. F doesn't have any neighbors, so yeah, so we don't know anything. Now we'll just, everything is done. Now if you look at it, okay, so we have F with the 9. Okay, so now what our question is, so our initial question was find the minimum distance between source and destination, that is A to F. So initially we already told that each node has the minimum distance from the source. So F is 9, so our answer is 9. Now if you want to see it, A to B is 1, 3, 3 and 1, 4, plus 2, 6, 7 or 2. This is the minimum distance. Pick any other node, you will find the largest. Like if you go via C, it's like 5, 6, it will be much costly. If you go via A, if you see A to B, if you go pick any other, it's like going to be costly, like 7, 8, the 10. Direct path is the like A to B, B to E, E to F is 10. So that is still the cheaper one. Okay, so now we know the distance. Let's say if the question comes, find the path. Okay, so we'll retrace back. Now F, that's where like via comes help us. So F is coming from, if we are table, we are saying like F has the minimum distance from the source, but that is coming via E. Now E has the minimum distance from source coming via D. D has a minimum source coming via C. C is coming via B. B is coming via A. So, okay, that's A, B, C, D, E. Okay, that's surprisingly. So that is our path. That is the shortest path from A to F, and that's the value sum of weight minimum. So this is how algorithm works. Now what we need to do is we just need to code this algorithm. Now let's start coding in the JavaScript. So we discussed the solution already. We have solved an example. Now this is one of the lead code question, which actually, like if we go to the question, we will see this actually the shortest path algorithm, and we can use any shortest path algorithm, and here we can use Dijkstra. So we will see. So if we see the question, it's a network delay time question. It has been asked in Google, Amazon, Microsoft. Google loves asking graph questions, so this is like, again, as in not surprising, asked in Google. So if you read the question, you are given a network of n nodes labeled from 1 to n. So the value of n varies from 1 to n. You are given time, list of travel time as directed is between time of I. So each like times of I, for each I it will represent UI, VI, source, destination, the weight of it. And we will send a signal from a device node K and return the minimum time it takes for all the n nodes to return the signal. So remember, return the minimum times it takes for all the n nodes to receive the signal. That means we need to find a node which takes maximum time, so that till it resets, all the other nodes must have received the signal. Okay, else we will return -1. So I think as we can answer this, a very straight, this is a simple question. If we find the minimum distance of all the one, and then we can find which has the maximum distance from the source, so eventually we will find it. Okay, so now we don't need to do anything, just remember what we have, follow the approach, we will do it. So here the representation of the times is different. So our representation, if you remember, so easy because remember we have a node, we will go over neighbors, so we will convert our data structure into that representation. So we'll use graph, like our graph adjacent list of that one. So we will create graph, create adjacent, so we will like create that graph. Yeah, because this is our first motive, right? So we'll give it times and n. Okay, so that's our first motive to create that graph. Now what we need to do is we will have a fun, we don't need to do anything, we will have a okay, why it's happened. Okay, my mind, I think refresh is not working. Let me refresh the page. Yeah, it's fine now. So we can call this function, we can call this, so this is times and n. So what we do is, so we'll create a map, adjacent list we can call it, and we can create in JavaScript through map. You can create use objects, but this is like just a more slightly easy way. So we will go over each time, and now remember what we need to do is, yeah, we already have the time array. Time is the array, so what we have is source, like start, end, and we have the here we can say, let's say, okay, so time, let's say we call it time arc. So we have the time taken between them. Okay, so now what we need to do is, we will check in the graph if we'll check our adjacent list. If adjacent list dot has start, if it doesn't have it, we will set in the graph, what we will set it, we will do start, and corresponding to that we will set the array. Okay, so once we do that, so that at least it will always be initialized. Now we need neighbors, and how we can get the neighbors is adjacent dot get. Okay, so I have the source, I need to, so I have the start actually, so I can get it. Okay, so the start node, I can get its neighbor initially, like it can be empty, I know it will empty, but later it might not be, so we can get neighbors. Neighbors dot push, sorry, pushing is, we'll pushing node, that is end, and we are pushing the time. Okay, yeah, so we'll be pushing the time, so each, so neighbors has a node and a time. So once we do that, we don't need to do anything, we can simply return our adjacent list from here. So remember, this is exactly like is easy representation. So once we do that, now remember what we need is, we need a visited array kind of thing. So we can create again a map, we need a path table. Remember the table that we discussed, we can create a table. Now the range, as we, if we see in the range below, it's like 1 to n, like k and n both vary from between 1 to 100, and also it's written that n nodes are labeled from 1 to n, so it starts from 1, so starts from 1 while I less than equal to n I plus plus. So here what we need to do is, just to make sure, wasted dot set I, we can make it false, but that's more important is our path table. So path table dot set, in path table, sorry, what we need to mark is, now remember, corresponding to I, what we have is two things is, we have the time, yeah, so we can actually have the minimum time, that we can mark it as infinity, and we can has a via, like which node. Okay, yes, so remember, this is the table visit, corresponding to each node we will have minimum time and via, like distance we are talking about. So here just to relate with the questions, to is easy. So once we do that, right, so remember, then the second question was to set the current one. So we have the path table dot set, we already have the current node given as us to us k. What we will do is, minimum time we will mark it as 0, and via we can mark it as k, like this will not be matter for us, right? So now what we need to do is find min time. Here we will pass n, we'll pass the current node, we'll pass the times, we have visited, we have path table, and we have create a graph adjacent list. So you can pass that. Now we can focus on writing the function find min time, where we have n, we have current node, we have times, we have visited, what else we have, then we have path table, graph adjacent list. Okay, now first we need to check if it is visited. Remember, like we need to make sure that we need to find like all the nodes should be unvisited, so just to make sure that so now where is visited? Yeah, we have a visited array. So visited dot has current node, that means it should be false if it is the case, or if we know, if like let's say due to any reason we get current node is out, this is like less than 1, which can't be the case, or current node is greater than k. Remember, it is just like doing simple, right? We can simply return from here, we don't need to do anything. Once we have it, we have this node. Now we can visit it dot set current node, we can mark this as true. Okay, we can mark this node as true. Okay, now we can do is, remember, now we have to find the neighbor, but for that, before, for the current node we need to find the minimum. So minimum time for current node. Remember the formula, you know, for current node, like from where this will come? This will come from the table, path table dot get current node. So if we look at the path table, where is our path table? Path table, this is path table, so it has minimum time, so we'll fetch the minimum time. Okay, minimum time. Now just to make sure, we can pass check, like if it is infinity, we can pass it 0, else we can, yeah, we can simply do it this. Okay, so we have the now minimum for the current node. Now we need to get the neighbors. How we will get the neighbors? We will get it from adjacent list, graph adjacent list dot get. From that we will get for corresponding current node. It has like array only, so but just to make sure, if this comes null, we can mark it as neighbors. Now we have the neighbors. Now we can iterate over it. For each, we can call it ne. Okay, now we need to call the new time, const new time. Okay, so that is the minimum time for current. Remember the formula, minimum current node plus the distance of that node, which will be having ne dot time. Now if you look, this is the time, like from neighbors are coming from graph adjacent list, and if we go to where is a graph adjacent list, it has, we are putting as node and times. Okay, so we are getting that time value here. Okay, now const existing mean time. No, what is the existing minimum time? Remember, like we need to compare it with the value which is already exist in the table. So we need it from path table dot get current node. We will read its value from the current node. Now dot, it has minimum time. If you see, this path table has minimum time, so we'll read minimum time. Okay, so here if we do, now what's the formula here? If new time is less than existing min time, or is existing min time, then what we need to do is, we'll update our path table dot set. What we need to update with nei dot node. Remember, we need to update new node because new node has a now minimum distance. With what we need to update it with, minimum time as new time, because new time is lesser, and we need to update our what other we have, what we are using here, via. Okay, so we are using via this is a current node, because from current node is the minimum distance. Okay, so once we do this for each neighbors, once we finish this with each neighbor, all our neighbors are finished. Now what we need to do is, remember, find new minimum from unvisited nodes. Okay, so we can do that. Let I is equal to 1, let min time is equal to infinity, let min node is equal to null, now we can run our loop while I less than equal to n I plus plus. Now here remember that condition. So if visited dot get I, that means if visited is true, we will continue this loop, we will not consider this, and before that we need to increase its value. Okay, so we can increase its value. If that is the case, that's fine. Else what we will do is, if path table dot get for current node dot path table has minimum time, right? So minimum time is less than equal to the min time. So what we will do is, we will update min time also, because we need to update our minimum, and we will update min node also. Because we already talking about the current node, we already have the node here, right? Yeah, so we update the node, and we will do this, and we will go to the next one once we do this. So if let's say minimum node, like if we don't find any minimum node that is equal to null, you can simply return it. Else where we are calling find min time, so we can call it find min time. We can call it again with only the, instead of k we will change it to min node. Other things will remain same for us. Okay, so if we do this, now our algo is completed. We have the path table ready. Now we need to focus on what's next. Okay, now we need to find simply the min time, our answer actually. So remember we talked about that, we in the end we need to find the minimum time it takes all the n nodes to receive the signal. So see, if it is like something like that, if one node is taking like 3 seconds, other is like 10 seconds, so minimum time will take on all the nodes will be where, like if the last node is taking the most time, that's the it's everyone has to wait, like all node will be completed, right? So once, because this one will take the largest time, will still remain it, other one will be filled. So what's the minimum time, so that everything will be completed it is the when the last one, the biggest one is filled, then we 100% sure other one are filled. So this is the minimum time. Okay, so we'll go with that. We will, because I think we already have I already declared, we have our answer. Okay, now we will go over while I less than equal to n, and now what we need to do is, now we need to check if path table dot get will get the current node dot minimum time. If any of the node actually still has the infinity, if path table still has the infinity, that means we can't reach that node, and that means you can't, because that's not possible to find the minimum time, right? So we'll simply return -1, else we'll do answer is equal to math.max answer or path table dot get I dot minimum time, and then we can simply return the answer. So let's just go over once again so that we know. So we just create an adjacent list. We have map visited. Okay, so we adjacent list, let's say adjacent list is fine. With adjacent list, let's say adjacent list fine, we get adjacent list. So we are just putting start and end time. This is we are getting from time arc. So if it doesn't have start, we'll put a start. We'll set getting from neighbors and pushing the neighbors node and time. That should be fine. So then we are just going to each node. We are setting our table to minimum time and via. Okay, so then we are we are having path table dot set path table dot set minimum time, and we are setting, now we are calling find minimum time. So if we see if visiting out of node, if the node is like out of value, we'll return it. We'll mark our node as true. We'll find the minimum. If you remember, like just to make sure, like we have 0. I mean, it should not be fine. I mean, it will always be a valid because we like always have the valid values here. We negate neighbors, we iterate over neighbors. We calculate the minimum time for current node plus the time for between those two, and we read it from path table. We'll compare them. We'll set if it is new time is less, and we'll update the current node. Similarly, then we'll find the minimum here. Like we'll talk about optimization later, but this is like one way. So we go over it, we find the minimum, and then call it. Okay, let's try to run it. Okay, so we have an error line 38. Let's see line 38. K is not defined. Yeah, we don't have the K current nodes. Yeah, it should be, actually we should talk about the out of range, right? So invalid left. Oh yeah, sorry. Yeah, it's a map we are doing, so we'll mark it as true. Okay, it seems to be going in, might be infinite loop. Yeah, it is going into infinite loop. So that's what I'm thinking now, where it is going into infinite loop. Okay, let's debug that where is the issue. So we created a graph, we have a visitor table, everything. So this should not be causing it. Let's first find what's exactly causing. Let's comment it and run it so that we know which actually is the one which is causing our like like our this is the one we are causing it. Yeah, I think there's a stupid mistake. Yeah. Yeah, so we got missing. Yeah, we got -1. Okay. Yeah, let's try to debug it. So I think so before minimum time, let's see if we are getting everything correctly. Okay, so console dot we can log here our graph adjacent list. Okay, and then we have path table, and then we have visited, just to make sure. Yeah, so if you see the first one that we have is graph adjacent list, so that's fine, right? 2 has a neighbor 1, and 3 which has a weight 1, time has 1, and 3 has a neighbor 4 which has weight 1. So that is fine. Path table is perfect and visited is perfect, so all these are perfect, so it should not issue till here. Let's go to yeah, we need to focus on our like shortest path algo. So if visited, yeah, actually visited dot, it should be actually visited dot get. So if visited dot get current node, yeah, actually, because value might be present, but we need to get the current value, it's true or false. So I think there's a one mistake. If let's say that solve it, okay, that still doesn't solve it. So we can get the current node, and then we are checking if it value is out of bound. So if less than 1 or greater than m, we are returning it, that's fine. So then we are setting true, then we are getting the time from path table. Path table dot get current minimum time. So if that is equal to infinity, we are 0, else we are simply putting the time. Then we are getting its neighbor from graph adjacent list. So that is fine. So I think, yeah, let's try to see console here. Yeah, so at least we will know like if it is coming or not. So what we need to do here is like we will put current node, and we will need see if it is getting the neighbors correctly. So if we see after x, it's getting, yeah, it's getting actually, see 2, it is getting neighbors. It's going to 4 doesn't have neighbors. It's going to 3 has neighbor, 4 with 1, and 1 doesn't have any neighbors. So it's actually going correctly. So no, doesn't seem to be have any issue there. So let's go over neighbor. So neighbor, we are getting the minimum time for current node, plus we are reading the time. So what is neighbors? Neighbors is from graph adjacent list, and graph adjacent list where we are putting node and time, right? So that's fine. Yeah, so existing minimum time we are getting from path table. Oh yeah, sorry. So we don't need to get from current node, we need to get it from path table. We need to get for any this node we are talking about, remember? So this new time, what's the like this new node that we have, and what's we call it? So this is coming from NEI is neighbors is coming graph adjacent list, and there we are calling it node. Yes, right, correct, node. Yeah, so with this node actually we get the minimum time. So then only we will update the current node. Yeah, if you see here it's doing right, we are doing there wrong. Yeah, so this time it got passed. So I think 2 very basic mistakes, still like it's as per according to our solution, we just need to remember it, right? And we have to debug step by step. Let's try to submit it. Yeah, so this goes accepted. Okay, so if you see, this is a very standard question. This has been a pretty famous question asked in Google, Amazon, Microsoft. And here if you see, I mean like if this question is asked in an interview, right, we don't need to do anything. This is a very simple question, you understand it, okay, that nodes are connected, this is a directed graph going to wait. Now even the minimum time it takes for all n nodes to receive the signal. So that actually gives you the indication that okay, return the minimum time it takes for all n nodes to receive the signal. Okay, so that's why you need to understand that okay, if it is n nodes are there to receive the signal from the on a single node, so you can now, if you remember our tape, like graph doesn't have too much algorithm. At least if you try to remember the algorithm, this shortest path algorithm, the Dijkstra algorithm, all the nodes in the table have the shortest path. You got it. Now minimum time taken for all n nodes to receive the signal, it all, you have all the time, right? You know, like if we go back to our example, if you remember the A to F takes 9 seconds, right? So if let's say that is the like F is taking 9, all the other nodes taking how much less time. So what's the minimum time taken so that signal will reach all 5? Let's say if we talk about 8, other nodes might have reached, but 9 still need to receive it because it will take 9 seconds to reach it. Once on the 9th second, we know the F has already the time, so it should not be an issue. Okay, so that's the algorithm. So we just need to practice it. If we have the grasp over it, it will be like easy to modify those questions and to understand it more. Okay, thank you, all the best, and keep following, keep subscribing. If you have any suggestions, feel free to comment. I will happy to like do better in the next video. Thank you.